Welcome to the Tower. I am your director for today's Air Traffic Control Exam Emergency Simulation. Now listen up, because today we are tracking a massive, high-tariff, incoming heavy aircraft right on our radar screens. We're talking about Cambridge AS and A-Level Mathematics 9709. And look, the difference between scoring a B and securing that A-star in this specific explainer, well, it isn't just about vaguely knowing the math, not at all. It is about understanding exactly, and I mean exactly, what those examiners are looking for when it comes to parallel, intersecting, and skew lines under extreme, intense time pressure. I want you to think of these 3D vectors as literal flight paths in our airspace. If you can't prove mathematically whether two of these flight paths are parallel, intersecting, or skew, you aren't just losing a couple of marks. In the context of our simulation today, you are risking a catastrophic mid-air collision. It's that serious. So I need you to strap into your console, completely clear your mental airspace of any distractions, and let's initialize the radar grid. We've got a lot of ground, or should I say air, to cover, and every single second counts.
Okay, let's really dive into this by looking at two of our radar operators handling the exact same approaching aircraft. Over on the left console, we have router Alex. Now, Alex represents our classic B-grade answer. When confronted with a high-stakes vector question, Alex kind of panics. He gets totally bogged down in the minor calculation details, creating this infinite holding pattern of superficial breadth. Alex is frantically calculating lambda and mu, just crunching numbers, but honestly, he has absolutely no idea what those parameters actually mean in the physical 3D space. He's just doing math blindly. Now glance over to the right console. That's router Sam. Sam is our A-star grade answer. Sam doesn't panic. Sam demonstrates incredible analytical depth and precise, razor-sharp definitions. Sam clears the arguments for landing swiftly, but, and this is absolutely crucial, Sam never does this without verifying the structural safety regulations first. You see, the academic benchmarks from Cambridge explicitly prioritize this kind of analytical depth over superficial breadth. You are simply not rewarded for just throwing numbers at the page. You are rewarded for structured, logical reasoning that proves, beyond a shadow of a doubt, that you completely control the airspace.
So, here is your flight plan for today's simulation. Number 1, core principles. Number 2, the method mark strategy. Number 3, critical evaluation tactics. And finally, number 4, top examiner warnings.
Let's move into Sector 1, Core Principles, the Theoretical Architecture.
You've got to realize that the assessment objectives for Mathematics 9709 do not just test if you can plug some numbers into a memorized formula. No way. They deliberately target distinct cognitive domains. We're talking about your foundational knowledge, your deep conceptual understanding, your practical application, and your high-level analysis. When you set two vector line equations equal to each other on that exam paper, you are communicating something specific to the examiner. You are telling them you understand that for these two flight paths to cross, specific parameters must exist that result in the exact same 3D coordinate at the exact same time. Now, hold on. An amber warning light just flashed on our console regarding terminology. Listen to this. Examiners consistently report year after year that candidates completely confuse key vector terms, and this leads to absolutely catastrophic point loss. So let's definitively clear up the most misunderstood flight path of them all: skew lines. What are they? Skew lines are vectors in 3D space that are neither parallel nor intersecting. I want you to picture this. Imagine one airplane flying dead north at an altitude of exactly 10,000 feet. Now imagine another airplane flying dead east, but way up at 30,000 feet. Are they parallel? No. They're heading in totally different directions. Will they ever intersect? No. Because of that massive altitude difference, they will never touch. They literally just pass in the night. In your exam, you must always mathematically define and prove terms like skew lines before you ever use them in your extended responses. You have to prove they aren't multiples of each other, and then you have to prove their simultaneous equations yield totally inconsistent parameters. That's how you lock down the airspace.
I need you to lean in and listen very, very closely to this next transmission. This is a massive insider secret pulled directly from the principal examiner reports. Think of those reports as the black box of Cambridge grading. The quote reads, "Candidates referencing cross-topic connections achieve significantly higher marks." So what does this actually mean for you sitting in that exam hall? It means the theoretical architecture of vectors doesn't exist in a vacuum. It rests on integration with entirely other syllabus areas. If you can elegantly connect your 3D vector analysis to, say, trigonometry, or if you can use your deep understanding of simultaneous equations flawlessly while evaluating intersecting lines, you instantly elevate your response from standard to truly exceptional. The examiners are explicitly telling you right here how to trigger their highest reward algorithms. Do not isolate vectors in your mind. Connect the flight paths across the entire mathematical grid.
All right, shifting to Sector 2, the method mark strategy. This is where we build your procedural framework.
We are now entering minute 4 of our simulation and the tension is rising. It is time to route the approach vector using what I like to call the fuel to mark budget formula. Here's how it works. In the Cambridge marking scheme, marks are awarded as a safety net for your process and your systematic analysis. They aren't just looking at your final coordinate. Even if you miscalculate a super simple arithmetic step, say the landing gear jams at the absolute last second, if your procedural framework is flawless, the examiners will absolutely still award you method marks. They want to see that you knew exactly how to land the plane, even if there was a tiny mechanical hiccup. Let's go back to Router Alex and Router Sam at the radar consoles. They're furiously debating the sequence of operations right now. Alex, panicking as usual, jumps straight to step 3. He's trying to guess the relationship between the vectors without even setting up the basic equations first. It's total chaos. Sam, however, takes a deep breath and follows the strict procedural framework. Step 1. Extract data from the question. Sam writes down the position and direction vectors crystal clear. Step 2. Apply correct formats. Sam sets up the line equations using distinct, separate parameters like lambda and mu. Step 3. Interpret relationships. Sam methodically solves the simultaneous equations for the first 2 components and then substitutes them into the third to draw a rock-solid, evidence-based conclusion. This disciplined, step-by-step approach guarantees you do not drop those easy process marks.
Now, we are looking at the explicit breakdown of exactly how your process is monetized into actual marks. You can clearly see the distinct phases, detailing the descriptive, analytical, and evaluative exam stages. But wait, before we clear this response for touchdown, tower transmission check. To ensure your radar transponder is fully updated for all future simulations, I need you to subscribe to Ace the Exams at the handle @AceTheExams right now. Seriously, hit subscribe and turn on all notifications so you never miss an incoming broadcast. Done? Perfect. Okay, let's retune the transponder and get back to the framework. Look closely at the required actions here. Extracting the right vector data, that gets you descriptive marks. Interpreting the simultaneous equations, boom, that gets you analytical marks. Justifying that lines are skew because that third equation completely fails, that gets you those sweet, high-level evaluative marks. The assessment framework literally guarantees marks for showing you're working out at every single level of the descent. It pays to show your work.
Now, let's say you're in the thick of it, and you suddenly encounter an unexpected structural block mid-paragraph, mid-calculation. Your simultaneous equations are looking incredibly messy. The numbers aren't making sense, and you literally feel yourself drifting off the glide slope. This happens to everyone. But this is exactly where strict presentation conventions step in and save your life. The director deploys the PEL formatting template to guide the sentence back onto the glide slope. You have to use proper headings, correct terminology, appropriate mathematical formats, and super clear annotations. Point, equation, evaluation, logical conclusion. If you are solving to check for intersecting lines, don't just write a jumble of numbers. Annotate your work. Write down solving for I and j components, and then write substituting into k component to check for consistency. This isn't just about making your exam paper look pretty. No, practical application develops professional skills. By clearly signposting your mathematical logic for the examiner, you ensure they can easily track your thought process and award you those hard-earned method marks, even if you accidentally mess up an addition or subtraction later on down the page.
Welcome to Sector 3, Critical Evaluation Tactics. It's time to test the quality of your evidence.
We are now actively shifting our focus to those higher-order assessment objectives. These are the ones that demand you evaluate alternatives, compare different approaches, and make totally justified recommendations. Listen, in vector mathematics, especially at this tier, it is not enough to just find a number and move on. You have to evaluate what that number actually means for the physical reality of those 3D lines in space. Are they on a direct collision course? Are they perfectly synchronized? Or are they entirely independent? Basic analysis is really just identifying relationships. Router Alex looks at a screen and says, well, the direction vectors are not multiples of each other, therefore they are not parallel. Okay, fine, that is basic. But critical evaluation? That is Router Sam taking it to the next level. Sam sets up the equations, identifies the mathematical limitations, checks for alternative interpretations, and evaluates the complete effect on the final conclusions. Let's do a live audience tracking exercise right now. Ready? I am putting a 60-second visual timer on the clock in your mind. Think about your own past paper answers. Be honest, are you just finding the value for lambda and then completely stopping? Or are you taking that final crucial step and explicitly writing out the final conclusion? Something like, because substituting lambda and mu into the third coordinate yields a clear inconsistency, the assumption that these lines intersect is mathematically false, thereby proving they are skew. That single, critical, evaluative sentence, that is exactly what secures the A-star.
Moving into Sector 4, the top 3 examiner warnings. Pay close attention.
Okay, we are approaching the runway, but the tower is detecting massive debris on the landing strip. These are the exact recurring errors that consistently cause top-tier students to crash and burn, dropping them straight from an A-star down to a B grade. We absolutely need to clear these hazards before we authorize your final approach. Warning number 1, confusing cause and effect. Students constantly state that lines are skew because they don't intersect. No, that is a logic failure. You must prove they aren't parallel first and then prove they don't intersect. It's a two-part definition. Warning number 2, forgetting to check format and presentation. This is huge. Using the exact same parameter variable, like using t, for both line equations simultaneously. That is a massive safety violation. You are basically telling the math that both objects are at the same place at the same time by default. You must use different variables, like lambda for line 1 and mu for line 2, because those lines operate completely independently in space. And warning number 3, answers not specific to the given context. If a question gives you coordinates representing real-world ships or real-world aircraft, do not just leave your final answer as some abstract naked math coordinates. Bring it all the way back to the specific context requested by the examiners.
We are under extreme time pressure right now, literally less than 3 minutes to touch down on this simulation. So, here is a quick interactive runway workshop challenge for you. Grab a pen. Seriously, grab one. To prevent terminology confusion when your adrenaline is spiking, you need a memory hack. I want you to create a mnemonic using the first letters of our key line properties: parallel, intersecting, and skew. PIS. Maybe something like pilots inspect skies or planes in space. Whatever works for your brain. Write down exactly what each step requires. P. Prove the direction vectors aren't multiples. I. Investigate those simultaneous equations. S. Substitute the values back in to check for mathematical consistency. Lock this mnemonic into your transponder right now. Memorize it. When the exam anxiety hits and your mind goes blank, this memory hack will completely autopilot your procedure and guide you home.
And safe touchdown. Router Alex and Router Sam have both logged a successful landing sequence. But because you actively followed the Fuel to Mark budget formula, your payload of points is completely maximized. You didn't leave anything on the table. So as we wrap up this simulation, I leave you with this final tower transmission. How will you actively adapt your own vector methodology starting today to secure those higher-order evaluative marks? Don't just let this explainer be something you passively watch and forget. Share your custom mnemonic hacks with your study groups. Get talking about it. And most importantly, before you log off your console today, make sure you subscribe to Ace the Exams at the handle @AceTheExams. Enable that notification bell, and I want you to leave a comment down below sharing which specific past paper gives you the absolute most anxiety. Let me know what you're struggling with, and we will clear that exact airspace together in the next simulation. You've got this. Tower Director, signing off.